I think one of the best ways just to get used to working with R is to learn how R can serve as a good replacement for your handheld calculator or maybe the one that you have on your phone. So that's going to be the point of today's video, is to look at how we can use R to do basic calculations, arithmetic, powers, logarithms, etc. And then also learn about the saving convention that allows us to define variables that contain numbers that we can use in our equations, in our computations. So just as a quick reminder, remember that you can always navigate to the relevant timestamps on the video on the bottom left-hand side. If you click on that more, you can get the table of contents, and you can always click the ... on the bottom right to open up the transcript and do a search for a keyword or a key phrase. So let's go ahead and get started with working with R for doing basic computations. And I'm going to load up an RMD file, MathProblems.Rmd, to give us just a nice place to play around and see how equations work. So we're going to start out slowly by using R just as a calculator. So when we do basic arithmetic in R, it's pretty much as you would expect. It can do multiplication, division, etc. Multiplication is that asterisk symbol, the shift 8. The division symbol is the slash command, where the question mark is. And the way that R evaluates expressions is with the standard Pemba's rule. So multiplication, division happen first, followed by addition and subtraction. So let's see how this goes. Let's imagine that we wanted to figure out what the answer to this equation is. So this is written in a funny language called LaTeX. You don't have to worry about the way these equations are structured in your RMDs. I'll be providing those equations to you. If you mouse over that equation, it'll come up with a nice, pretty looking equation for you. So let's translate this into R. Basically, we want to take 7 and then add 5 times 10. And then subtract off 200 divided by 4. The only thing we need to know is that multiplication is that asterisk symbol and division is that slash symbol. So once we've typed that, remember a few ways to shoot this down into the console to see what the result is. My favorite is Command Return on a Mac or Control Enter on a Windows machine. And we'll see that down in the console, it lets us know that it's 7. And also you'll notice that it's embedding the result in the RMD file. Normally, I don't like it being embedded in the RMD. I just want to see it down in the console. So we can always go to the gear icon and say, hey, let's chunk output in console. And it'll ask if we want to remove that output, and yes, we do. So normally when we do evaluation of expressions, it's that multiplication and division first, followed by addition and subtraction. Well, what if we actually wanted to add the 7 and the 5 together first, and then multiply by that 100? Well, that's going to be the job for parentheses. So we'll be using parentheses a lot in this course, and parentheses allow us to force the evaluation of a certain expression before normally doing those Pemba's rules. So if we were to go and look at our equation, we want to take 7 plus 5, add that first, multiply by 10, then subtract off 200 divided by 4. And I can do so fairly quickly. If I copy and paste, I can just wrap the 7 plus 5 in a set of parentheses, and that's going to force R to evaluate that first. So another way to shoot this down into the console, we could click Run, and we could say current line, that's where my cursor is, and notice that we get the result of 70 out. All right, some additional practice using parentheses. Here we want to take 4 and multiply that by 1 plus 8. And then we're going to add that to 15 divided by the quantity 5 minus 2, 5 minus 2 being in the denominator. So let's make sure we use parentheses so that R evaluates this expression correctly. So we'll take 4 and multiply that by 1 plus 8. That's the easy one. And then, because we have an expression in the denominator, when I take 15 and divide it by that expression, I need to make sure that expression is in parentheses. So when I evaluate it, I get 41. Notice how the result would have been a bit different if I were to copy and paste this and just leave off that set of parentheses. What's going to happen is that R is going to divide 15 by 5 and then take that result, 3, and subtract 2 from it, and I'll get a very wrong answer. So we need to make sure that if there is a certain operation that we need to have R evaluate first, put that inside the parentheses, and we'll be using that a lot when we raise things to a certain power, when we run special functions, etc. So parentheses are our best friend for making sure the computation proceeds as we want to. Now, one thing we want to be aware of when we're using R as a calculator is the multiplication symbol, because very often as shorthand, mathematicians write products without necessarily writing the multiplication symbol, 5 times the quantity, 3 plus 2. Now, R is not smart enough to follow that heuristic, that convention that mathematicians carry with us. If we do need to multiply things together, we have to have that multiplication symbol. Otherwise, R doesn't know what's going on. Now, we can see that with this example here, with this viral meme that kind of broke the internet. You might remember the math equation saying, hey, what does this evaluate to? And people just could not come up with the correct answer because they had forgotten PEMBA's rules here. Now, if we were to just try to put this in R, 8 divided by 2, and then 2 plus 2 in parentheses here, what's going to happen is that R is going to come back with an error saying, hey, attempt to apply a non-function. That's because if we have a set of parentheses that immediately precedes either a letter, a word, a number, or something, it's going to assume that we're trying to run a function like mean or LM or median, etc. So if our intent is to actually do that implicit multiplication, we need to make sure to tell R to do that multiplication for us. So 8 divided by 2 times the quantity 2 plus 2, and we can see that it evaluates to 16. And going back to that viral meme, normally what people did is they said, okay, well, let's do the 2 plus 2 first. That's going to be 4. Multiply by 2, that's going to be 8. 8 divided by 8, that's 1. Wrong answer. So R is going to be able to get us there with no issue. Just got to make sure those parentheses and multiplication symbols are there. All right, what other common mathematical operations do we do in R? Well, we very often raise things to a certain power. Maybe we'll square 5, 25. Maybe we'll take 2, raise it to the minus 3 power, equivalent to 1 over 2 raised to the third power, or 1/8. So how do we do exponentiation in R? Well, what we're going to do is we're going to use the caret symbol, the shift 6, to represent that exponentiation. So let's imagine we wanted to evaluate 2 raised to the 4th power, and then add that to 4 raised to the minus 2 power. And if you remember your laws of exponents, raising something to the minus power is essentially the same as taking the reciprocal of that quantity raised to the positive power. So 4 to the minus 2, same thing as 1 divided by 4 squared. So in R, how do we do this? To take 2 and raise it to the 4th power, we separate the 2 and the 4 by the shift 6, that caret symbol. That's going to give us that 16. And if we're going to add that to 4 raised to the minus 2 power, well, what we're going to do is, because we have more than one symbol in our exponent, we're going to wrap that in parentheses to make sure that R is treating that appropriately. So when we run this, we'll get 16 plus 1 divided by 4 squared, 16.0625. Here's some additional practice. Whenever we have a complex exponent, more than one character, it's a good idea to wrap that exponent in parentheses just to make sure that R is evaluating it appropriately. So here what we're going to do is we're going to take the fraction 5/2 and we're going to raise it to the 3 minus 8 divided by the quantity 6 minus 3. So we're going to have to be very mindful of these parentheses to evaluate this correctly. First, let's start out by taking that 5/2 and then raising it to the power requested. And because this is a complex exponent here, I'm going to put a set of parentheses, maybe give it some spaces here, and I'm going to write that exponent appropriately. So we're taking 3 and then subtracting off 8 divided by 6 minus 3. Now, because 6 minus 3 is in the denominator, I need to make sure that's inside its own set of parentheses. Short, cool trick for this: if you highlight something you want to put in parentheses, shift 9 to put those parentheses there. It puts the left and the right there. Kind of a cool trick that R does. And so now I've evaluated that exponent appropriately, and I can shoot that down to the console, and I see that it's equal to about 1.36 or so. And this raises another interesting point that R respects. It doesn't really care about how many spaces you put in between your expressions. So notice I can put in a whole bunch of spaces here, and R is like, that's fine. I'm going to evaluate this as you won't really want me to. And so we can choose how we want to represent our equations, to our liking. So normally I like putting it so that everything is nice and neat. I don't like putting spaces if I don't really have to have them, but that's a choice. If you think adding in spaces is going to make your code more readable, by all means, put in those spaces so that it kind of matches your own personal style. All right, so there's some exponents that there are shortcuts for. So very often if we want to take the square root of a number, taking the square root as raising it to the 1/2 power, we can just invoke the function sqrt. So if I want 5 plus the square root of 16, I could write that out as sqrt of 16 here. I get 9. Square root of 16 is 4. 5 plus 4 is 9 here. But of course, I could have done this as 5 plus 16 raised to the 1/2 power, or even 5 plus 16 raised to the 0.5. I could just simplify that to be a decimal. I get the same answer regardless. All right, well, let me throw a little wrench in this. So here, I want to take the square root of 3 plus the absolute value. That's what the pair of bars are representing here, the absolute value of 2 minus 10. And then I want to take that result and round that to 2 decimals. All right, well, how would I actually go about doing this? Well, let's not worry about the rounding quite yet. Let's take the square root by invoking the square root function, and then transcribing inside those parentheses what I want to take the square root of. 3 plus, and to get the absolute value, you might have guessed it, just ABS, and inside that function we'll put in 2 minus 10 here. We evaluate this, it works out to be about 3.3, but I need this result rounded to 2 decimals. And you might be a lucky guesser and say, well, why don't I use the round function? That could be something that R knows about. And you'd be right. So if we put this inside the round function, it's going to go and round this expression to a certain number of digits. Let's just run this as is, and it rounds to 3. So here's what you're going to do quite often when you're working in R and using functions that are going to be doing stuff to expressions. You might need to load up the help menu for a particular function so that you understand how it works. So I always do the question mark and then the name of the function down in the console window. I don't like putting that up in the RMD file. It doesn't allow you to knit when you have that there. And when I do question mark round, I get the nice help menu that lets me know, okay, here's how this function works. Usually fairly cryptic. It's designed for advanced readers. Well, here we go. So round is going to take a argument x, which is just a numeric vector, or just a number, and then a second argument, digits equals. And its default is 0, because we see in the definition it's set equal to 0 if I leave that out. And we see that this digits is an integer indicating the number of decimal places or significant digits to round to. So if I want to round to 2 digits, well, why don't I try digits equals 2 here? So I'm going to copy and paste this and just add in, after I've done the square root, but still inside the parentheses with round, digits equals to 2. And when I do this, brilliant, 3.32, I've rounded it to 2 digits after the decimal point, and so I've successfully completed my task. All right, well, let's talk about logarithms. So logarithms are things that we use a lot in analytics. It turns out that it's a bit easier to analyze a lot of quantities on the log scale because so many quantities in analytics are highly skewed to the right. If we think about data usages on people's cell phone plans or internet plans, if we think of savings account balances, incomes, it's going to rise up to a peak fairly quickly and then take its time to fall off. There's going to be outliers, really large values, etc. They're all going to be positive, and very often that's what we see in analytics. And so it's our choice as analytics practitioners to basically decide what we're analyzing, the raw data values directly, or we can analyze something related to them, like the logarithms instead. We'll be doing that in the regression class actually quite a few times. So we need to know how we work with logarithms in R. So one thing that you might be familiar with from math class is the abbreviation ln for natural log. Now R does not know this abbreviation ln. If I were to go back to RStudio and type in the natural log of 123 here, I'm going to get an error that says error could not find function ln. That's actually not the way that R takes the natural logarithm. Instead, to get the natural logarithm of, say, a number 123, I'm going to use the function log. So that is its abbreviation for the natural log. Works just fine. And if I need to take the log in a different base, what I can do is type in that base as an additional argument, or because most of the time I'm working in log base 10, I can use the function log 10. So there's a log 10 of 234, and if I wanted to add these two together, easy to just separate those with a plus sign. I find that's a little bit below 7.2. All right, so complementary to logarithms are, of course, e being raised to a power, kind of the opposite of the natural log. So when we get into models that predict probabilities, let's say of making a purchase based on someone's income, we're going to come up with a model that tries to predict the probability based on a certain variable. So predicting the probability of purchasing based on income. And our equations are going to use e and raise it to a certain power. So we might see something like e raised to the minus 1.2 divided by 1 plus e raised to the minus 1.2. So it's important to know how we take e and raise it to a power. It's not actually by doing the exponent, the shift 6, the caret, which is what we use to raise everything else to a power. Instead, there's a special function that's going to allow us to take e and raise it to a power. And that function is just going to be exp in parentheses. So if I want to evaluate e raised to the 2 plus 1.9 power, I'm going to type out exp and then in parentheses what that exponent is, 2 plus 1.9. And then here I'm going to divide this by a pretty big numerator, so I'm going to wrap that numerator in parentheses here so it evaluates that correctly. 1 plus e raised to the 3 minus 1.2 power. All right, so what does the little e actually represent here? Well, it's related to scientific notation. If we want to write numbers in scientific notation, basically something times 10 raised to a power. So the e is really just short for saying, okay, this represents times 10 raised to a power. So if I were to take 3984000, if I were to write that in scientific notation, move the decimal place over to the left a total of 6 times, so it's right after the first non-zero digit, 3.984 times 10 to the 6th power. The way that I would actually write that in R is by saying 3.984 E6. So if I were to go back to RStudio and say, okay, let's go ahead and write that number, any number, 5.4 times 10 to the 6, 5.4 E6 is going to get me that 5.4 million, 5400000. So writing things in scientific notation, really not too bad. We just want to make sure that we know how to understand the result when we see that in R. If I were to type out 143,000, no problem. If I were to type that with that one additional digit, no problem. If I keep adding digits, though, R eventually is going to say, hey, let me help you out. Let me write this in scientific notation. So when we see the E plus and then something, that's just shorthand for times 10 raised to this positive power. Likewise, for a number much less than 1, 7.244 times 10 to the minus 8th power. Minus 8 just means, hey, there's a lot of zeros before that first non-zero digit. It's a number much smaller than 1. So that's how we do basic arithmetic in R, scientific notation, logarithms, absolute values, rounding, etc. And so what else should we know at this point before we dive any deeper into actually doing coding in R? Well, first things first is that we should be commenting our code whenever we can, if it makes sense to do so, because I guarantee you, after you've written code, you've walked away for a few hours, you've come back, you might actually you might forget what that code was trying to do. So if we do want to add comments to code, super easy. We start this out with the hashtag and we just write whatever we want. So we're writing out that we're playing around with scientific notation. Notice that it gives a different color. It's not going to evaluate this as a command. If I try to run that, it doesn't really do anything. It just skips to the next line here. So we can write comments after a line of code, actually. So I could say, making 5.4 million. Making 1.43 billion. So we can put hashtags and then comments on lines all by themselves, or we can put that anywhere else we want to on a line. R basically just stops evaluating that line whenever it runs into the hashtag. So if I were to highlight this line, Command Return, Control Enter on Windows, it's going to go ahead and just evaluate what it sees before the hashtag, and it's going to give me that 1.4 E plus 09. All right, so normally, using R as a calculator is great. That's what I do instead of bringing out my phone or taking out a handheld calculator. But very often the computations that we're going to create in R are things we might want to reuse a little bit later. So maybe we would like to save the result of running some sort of computation into some sort of variable, like X or dog or Cannon or Jackson. They're roaming around here right now. So let's talk about how we save results and what that really does for us. And to motivate this, here's a question for you. So let's imagine we're working for some advertising analytics firm, and they would like to study the spread of word of mouth. So how many people have heard of this product if people are telling each other, more people each day? So maybe one thing that we know about this spread is that the product ad actually reached originally around 300 people here. And then we're going to assume that each day, just through word of mouth, the number of people that hear about that product doubles. But then 50 people that had previously heard about it are going to forget. Maybe like me, I forget things all the time. And so what we're going to have is this doubling and then subtracting 50, doubling, then subtracting 50 for a couple days here. We'd like to know how many people have heard about that product after 5 days. Well, how would we do this? Well, we could just start coding this to kind of mimic this process. Originally, we start out with 300 people. We double it and then subtract 50 after that first day. We're at 550. Then we take 550, multiply by 2, doubling it for the next day. Then 50 people forget, 1050. And we could continue to do this for quite a few days. And we could get to that computation just fine. And, if we're comfortable doing this, writing out a lot of code to get there, there's no shame in that. But let's try to do this a bit more efficiently. So why don't I create a variable x that stores the number of people that have heard about this product? So I would like to essentially take the number 300 and create a variable x that contains that value. How do I do this? Well, what we're going to do in R is to use the left arrow convention. So if I do want to define an object in the global environment, whether it be a variable, a vector, a data frame, etc., what I'm going to do is come up with a name for that object that I want to create, maybe just x. Then I'm going to use two symbols, the less than symbol and a dash, basically the left arrow. And then I'm going to give it some expression that I want that variable or vector, data frame, etc., to be defined as. So let's see how this works. If I were to go and do x left arrow 300 and then run this as a command, notice nothing really gets shot down into the console. No computation took place. Instead, what happened is that I now find x in the global environment. It equals to 300. So if I were to run x just as a command, essentially printing to the screen what's currently the contents of x, I do get 300 out into the console. But this suggests a nice, easy way to actually mimic the spread by word of mouth. So day 1, x people have heard about this product, 300 in this case. Then 2 times x minus 50, that gives me what happens on the end of day 2. And in fact, why don't I take that number and store that back into x? Let's overwrite the current definition of x with double its original value minus 50. And R is able to do this. The way that it evaluates an expression that has that left arrow is it notices the presence of the left arrow itself and says, okay, first thing I'm going to do is to evaluate what's on the right-hand side of that arrow. I'll see what this equals, and I'll take that quantity and I'll left arrow that into my variable x. So I know, if I just highlight 2 times x minus 50 and run that as a command, that works out to be 550. If I run the entire line, if I redefine x to be this, I'll see it being updated in the global environment. So that's after day 2. If I run this line once again, it's going to take the current value of x, 550, multiply by 2, subtract 50 out. We see x gets updated in the global environment. And I can actually just keep on running this command to see what it would look like after 5 days, 6, 7, 8, 9, 10, 11, 12. I could actually keep doing this. All right, so one last thing that I want to go over before we're done is the notion of printing something to the screen. I just mentioned that a couple of seconds ago. And in the homeworks and the activities, what you're going to find is that the way we want you to be writing code, we want to make sure that when you knit it, the contents of the variables you're creating, the results of your analytics, are getting automatically embedded into that Word document. And we do that by printing something to the screen. So a few final things before we wrap up. When we do name an object and use that left arrow convention, those names are going to be case sensitive. So right now, if I print out the contents of x to the screen, I get the following vector. If I were to use capital X, and let's say left arrow the result of adding 5 and 8 together, we'll notice that x is a different value than little x. 2 different values in the global environment. So you'll just have to be very careful when you come up with names. They're case sensitive, and we'll be able to respect that. And then finally, let's talk about commands versus functions. Now, these are 2 words we're going to use interchangeably, and we're going to be using functions and commands a lot in this class. We'll be using the LM function to fit a simple linear regression model. We'll run the check regression function in order to see if running regression was a smart thing to do. We'll use the associate function in order to figure out if there's an association, let's say, between the probability that someone makes a purchase and their income. Remember that in order to run the function, you have to give some parentheses after the name of that function, and then give the function some arguments, something that the function needs in order to run. So we talked about the absolute value function, the ABS function. It just takes a single argument. What number do you want to get the absolute value of? Log, which we know we can use to get the natural logarithm, actually takes two arguments, one of which is optional. The first argument of log is, of course, what you are trying to get the logarithm of. So the log of 30, let's say, works out to be 3.4. But it turns out that if I bring up the help menu, $log, we can see that the usage of this says, okay, hey, I could add in this second argument called base, if I wanted to get the log in a different base. Notice this is optional because if I go and look at the function definition, if I see an equal sign, R has provided it with a default value of that argument, meaning I can completely omit it and it'll use the default. So by default, it's using the natural log. But if I did want in log base 10, I've got that. If I wanted it in log 3, why not? I've got that too. So functions will be taking arguments, and it's important to give it all of the arguments that it expects. Otherwise, you might get an error out. Key thing is, if you don't know how a function works, go ahead and type in that question mark and the name of the function down in the console itself. So you don't want to be doing it up in the RMD file. It won't allow you to knit if you actually have a question mark in there. And there you have it. You should be good to go.